Yeah, so thanks so much for the opportunity to be here. And yeah, I'm sorry that I could only be here for today, but it seems like a really great program, and I'm going to tell you a little bit about algorithms for simulating quantum mechanics with quantum computers. And I understand that there was maybe some discussion of this topic in Ewan Tang's talk earlier in the week, but hopefully there'll be a different perspective on some of these questions. Great. Okay, so it's become, I think, kind of a cliche to show this quote when you give a talk about quantum simulation, but I really like it, so I'm going to show it anyway. I guess the idea of quantum simulation is really, really kind of at the origin of quantum computing. It was the thing that people looked to that really inspired the idea of building a quantum mechanical computer because of the difficulty of simulating quantum mechanics with classical computers, and the idea that if you built a computer that was itself quantum mechanical, it would be kind of naturally suited to simulating quantum physics. And so there are sort of two senses in which you can kind of think about trying to use quantum devices to get a handle on quantum physics, that people, both of which have been considered extensively. One of them is sort of the idea of kind of mocking up a quantum system with another quantum system, sort of building a system whose Hamiltonian, describes the kind of system you're interested in, and then using that as sort of a laboratory for understanding your system. So this is what goes by the name of analog quantum simulation. And so what I'm going to be talking about in this talk is sort of the other kind of quantum simulation, which is digital quantum simulation, where the idea is that we're going to build a fault-tolerant quantum computer that's really well controlled, where we can execute arbitrary quantum circuits on it. We're going to try to run some quantum circuit consisting of some quantum gates that we choose in order to understand the dynamics of some quantum mechanical system, some Hamiltonian that we would like to understand. So that's sort of going to be the focus today. Okay, and so what I would like to do is, sort of give a little bit of background of this problem, talk a little bit about why we care about it, and then talk a little bit about some kind of complexity theoretic issues related to Hamiltonian simulation. Then I would like to describe two main kind of classes of quantum simulation algorithms, one having to do with what are called product formulas, or trotterization, sometimes this is called. And I'll also talk a bit about sort of alternatives to that approach. So this trotterization idea is sort of like maybe the simplest and most natural approach to quantum simulation, but there are a bunch of other methods that have been developed that achieve better performance in various senses, and also involve some kind of nice theoretical ideas. And then, time permitting, there probably won't be time, but if there's time, I might cover some kind of special topics related to Hamiltonian simulation, and just say something at the end about sort of like maybe where things are going. Okay. All right, so I think there are several kind of reasons to care about quantum simulation, simulating Hamiltonian dynamics with quantum computers. The kind of obvious one is that we want to understand physics. So we want to understand chemistry, or materials, or particle physics, or some kind of domain in which there are quantum mechanical effects. The idea being that if in some system where there are strong quantum mechanical effects, we kind of expect in general that it will be difficult to simulate those systems with classical computers, but if we build a quantum mechanical computer, we'll be able to simulate those systems efficiently. Now, in doing this, we're kind of up against lots of sophisticated methods that have been developed to approach these systems with classical computers. There are many things actually that can be done already classically to get useful information, even about systems that are quantum mechanical. So it's not so obvious for these applications where exactly you can get a quantum advantage from building a quantum computer and doing a simulation quantum mechanically. But in any event, we would like to develop the most sophisticated tools that we can for doing these kinds of simulations with quantum computers. Okay, that's sort of like the obvious reason, but I think there are also some other reasons to think about simulating Hamiltonian dynamics on quantum computers, aside from just the fact that we're interested in simulating physics. So I just want to mention those briefly. One is that these tools can be useful for implementing other kinds of quantum algorithms for problems that maybe have nothing to do with physics, or that don't have an obvious connection to physics. So there are a bunch of quantum algorithms that have been developed, for example, for evaluating Boolean formulas, or for getting some kind of quantum description of the solution of a large system of linear equations, or other kinds of problems where the problem itself is not somehow inherently quantum mechanical, but there's a way of describing the problem in terms of some Hamiltonian dynamics and by simulating those dynamics, you can find a solution of the problem. So this is another application of Hamiltonian simulation. And finally, you can think about sort of using ideas related to Hamiltonian simulation algorithms without ever building a quantum computer, but just as a theoretical tool that you can use to reason about, physics, right? So at some level, if you have a quantum simulation algorithm, that's giving you some kind of, hopefully useful description of the time evolution operator of your quantum mechanical system. And so maybe you can sort of, use insights that come from these quantum simulation algorithms to tell you things about physics. So, I can mention just like one example of something like this, and I would like to see more examples of things like this. But so we have this paper that we wrote about sort of locality in quantum mechanical systems. There's this notion of Lieb-Robinson bounds, which describe sort of limits on the propagation of information in quantum systems. This particular paper is about that, these kinds of bounds, specifically in the case where you have power law interactions, interactions that decay like a power law. And in this paper, we developed better Hamiltonian simulation algorithms for systems that have these power law interactions. And actually, Lieb-Robinson bounds are useful for giving those simulations. But we also kind of turned things around and showed by thinking about the structure of a certain kind of Hamiltonian simulation algorithm that we could actually prove better Lieb-Robinson bounds for certain kinds of systems in certain regimes. And it was really through sort of thinking about how you would do the Hamiltonian simulation for this system that we were actually able to improve our understanding of, basically some aspect of the physics of the system. So, I think hopefully there's a future for doing this kind of thing. And I guess it's another reason maybe to be interested in understanding algorithms for simulating Hamiltonian dynamics. Okay. All right, so what is the problem that we're trying to solve? Well, it's really just understanding, what are the dynamics of the quantum system, which are, of course, determined by its Hamiltonian. So I guess this, concept is very familiar to this group. So, we have, in most of the cases that we're going to think about, we have maybe a time-independent Hamiltonian, and then the evolution is very simple. It's just, given by e to the minus iht, where h is the Hamiltonian. More generally, we can think about the case where the Hamiltonian has some explicit dependence on time, and then it's maybe not, there's not quite as succinct a way to write down what the time evolution operator is, but it still exists, and you can sort of reason about it. And so this is the problem that we're going to be interested in, is sort of understanding this time evolution of the system. So this is what I'm going to call the Hamiltonian simulation problem. In this problem, we're going to be given some description of the Hamiltonian. There are different ways that the Hamiltonian could be described, and I'll say a little bit more about that in a minute. But you'll be given some kind of description of what the Hamiltonian of your quantum system is. You're going to be given some evolution time, some amount of time you would like to evolve for. You're going to be given a quantum state that's the initial state for the dynamics. So that, in this problem, the way I'm describing it, will be provided as a quantum mechanical object, right? So this is something that's going to be loaded into the memory of your quantum computer. It's not necessarily something that you have a concise description of. I mean, it could be. It could be that you have some concise description, and that allows you to prepare the quantum state. But what you're really going to need as an input to this computational problem is a copy of the quantum state sitting in the memory of your quantum computer. And these algorithms will work even if you just have a copy of the state in your memory. And then the goal is also going to be a quantum mechanical thing. It's just to produce a copy of the final state, the state psi of t that you would get by evolving according to Hamiltonian for time t. Only approximately. So we're only going to demand that you can produce that state, let's say, up to some error tolerance epsilon. So that's also going to be a specification. That's also going to be a parameter that's specified, in the input to the problem. You would like to produce the state to within some epsilon, and you're kind of required to produce a state that's epsilon close to the actual output. Okay. So we have to think about how we're going to measure error, and for most of the work that I'm going to talk about in this talk, and for most of what's done in the literature, although this is not exclusively the case, we're going to think about sort of the worst case L2 distance. So we're going to ask that somehow the norm of the difference between the state that we prepare, so that's this psi sim, and the actual time evolved state psi of t, that this is at most epsilon. And we're going to think about algorithms that will achieve that guarantee, that will be within epsilon, regardless of what the initial state is, right? So we would like it to be that in the worst case, in other words, for all initial states, this is going to be at most epsilon, right? So the largest this distance can ever be is epsilon for any initial state. So of course, this is just nothing but the spectral norm of like the difference between the actual evolution operator and the evolution operator that you implement on your quantum computer, right? So we want that to be at most epsilon. You can definitely consider alternatives to this notion, like we can talk about what happens for particular states or states living in some particular subspace, or what happens on average when we choose the state from some distribution. We can use different sort of metrics to measure the distance between these states, and there are definitely results, and maybe if there's time I'll even mention some of them that think about these different scenarios, but this is maybe the most sort of standard one that's shown here.
You wouldn't at least want to be stable if they're taking the tensor product something else. I guess maybe
Right, right, yeah. So in this case, the evolution is unitary. We're thinking about sort of a case where the circuit is unitary, and of course the thing that we're trying, ideal thing that we're trying to do is unitary. So it doesn't actually make a difference. Yeah, yeah. So in general, if you have quantum operations, then it can be that somehow like the norm of the difference of the channels is close, but the channels are actually very distinguishable if you have the ability to act on part of a larger system. But if the action is just unitary, then it actually doesn't make a difference. You can show that somehow like this is like up to a constant factor, like factor 2 or something like that, related to the diamond norm distance of the associated channels.
But say that your simulation has some.
Yes. Yeah, exactly. Right. So that's a kind of situation in which maybe you would want to use, let's say, the diamond norm. Another scenario where that might happen is maybe your algorithm actually is not a unitary thing. There are algorithms that sort of make random choices, and maybe if you forget the randomness, then you really should be describing what the algorithm is doing by a channel, and then you probably do want to analyze things in terms of the diamond norm. So yeah, that's totally something you might want to do. Yeah. Yeah, Frank.
It's not always natural to require the protocol fidelity. If there's more like a fidelity per distance or something like that.
Yeah.
Does that fit in that framework? Can you kind of define the norm that quantifies that?
So, I'm not sure that I understand exactly.
To reproduce, let's say, all kind of n-body margins.
Oh.
Not just let's say all 3 body correlations.
Right. Yeah. Yeah. That's. Yeah, for sure. Yeah. I mean, I think there is some work on, let's say, simulations that will, just get right sort of measurements of local observables, let's say. Yeah, that's also totally a thing you can do. I don't know exactly, like, yeah, what is sort of the right metric to use in that case, but I think that scenario is definitely interesting and I think has been studied.
Look at the state on all subsystems of size order 1.
Sure. I mean, you can definitely write something down. Yeah, I guess. Yeah, for sure. Okay. Cool. Other questions? Okay, great. Yeah, so I really don't mean to be, prescriptive that somehow like this is the only way to measure error. Just that this is sort of like the most obvious thing, and it's the thing that's done in sort of a lot of work on algorithms for this problem. And then our goal is to understand what is the cost of simulating the dynamics as a function of various parameters of the problem. The ones that I'm going to focus on here, where there's been a lot of work, are the amount of time that you evolve for, t, and the amount of error that you allow, epsilon. And you also might be interested in how things scale with various parameters describing the Hamiltonian, like, for example, how many qubits does it act on? How local is it? How sparse is it? If it's a local or a sparse Hamiltonian, we'll talk about those notions a little bit more later. Some kind of parameters that describe the Hamiltonian. And we can measure this cost in various ways. Usually the thing that we're going to focus on is the number of gates or the circuit size in the circuit for implementing the simulation. But of course, you can focus on lots of different quantities. And in some cases, it's useful to think about query models for Hamiltonian simulation problems. And sometimes results about sort of query complexity for Hamiltonian simulation can be useful for getting a handle on the complexity of things. And we'll talk about examples, things like this in a bit. Okay, so I'm really going to focus here on just this problem of reproducing the dynamics of the system, kind of implementing this time evolution operator. But of course, if you actually want to do a simulation that's going to be useful for something, you have to think about how did you get that initial state? What measurement did you make on the final state that you prepared? If you're simulating some system, for example, that's made up of fermions, how do you encode these fermions into a system of qubits that a sort of ordinary quantum computer would be built out of? So there are many of these kinds of issues that one has to face in sort of thinking about how to actually apply Hamiltonian simulation to a real problem. But I'm really just going to focus here on the problem of reproducing the dynamics for some specified Hamiltonian. Okay, so for some specified Hamiltonian, but how are we going to specify what the Hamiltonian is? So we have to have some kind of description of the Hamiltonian that kind of specifies the problem. So one very natural setting that's been considered a lot is just the setting of local Hamiltonian. So we're going to say that a Hamiltonian is k local if you can write it as a sum of terms, each of which acts on at most k qubits, non-trivially. And this is a very natural setting because a lot of the Hamiltonians that arise in physics are fairly local with some some small value of k will allow us to describe the kind of models that we care about. If we consider a local Hamiltonian, then we can give an explicit description of what the Hamiltonian is. We can really just write out all of the terms as long as k is not too large. If k is like logarithmic, let's say, in the number of qubits in the system, then we can just give an explicit description of the Hamiltonian, and that will be a kind of a polynomial size object. And it also, the decomposition into terms that we get from having, writing H as a sum of these local terms is going to be very useful in Hamiltonian simulation algorithms, as we'll see shortly. There is also, however, a kind of more, oh, yes. Right, so according to this definition, it's not what you might call geometrically local, that somehow there's like a lattice and you only have interactions between qubits that are nearby, but that is an additional condition that you could impose. And actually, some of the results that I probably won't have time to talk about at the end are specifically about that case. Like, what can you say when your Hamiltonian is geometrically local? And you might expect that you could give more efficient simulations with that additional condition, and indeed you can. Like basically because of these like Lieb-Robinson bounds that I mentioned before. Basically because there's some locality to the physics of the system. Yeah. Good. Okay, so yeah, but there are also there's also kind of another natural class of Hamiltonians that's actually bigger than this class of local Hamiltonians, which are what we call sparse Hamiltonians. And most of the results that I'm going to talk about, can be applied also in this more general setting. So by a sparse Hamiltonian, I just mean that we have, the Hamiltonian is a matrix. It's a big Hermitian matrix. If we have n qubits, it's a 2 to the n by 2 to the n Hermitian matrix. We're going to say that it's d sparse if it has at most d non-zero entries per row. And since it's Hermitian, that also means it has at most d non-zero entries per column. So what that kind of intuitively looks like is we have some matrix where most of the entries are 0, and then we have just a few non-zero entries spread throughout the matrix. And to make this kind of useful for simulation, I mean, of course, you can't in general give a polynomial size representation of kind of a general sparse Hamiltonian, but we're going to sort of have another condition if we want to give efficient simulations, which is that we can efficiently determine where the non-zero entries are in any given row. Right? So if we're given a function that allows us to compute for a given row, where are the non-zero entries or what are the values for those non-zero entries, then it turns out we can use that to give an efficient simulation of the dynamics of this Hamiltonian. Right? So we can sort of like specify a row and we can find out where the non-zero entries are. So this is like just a more general class of Hamiltonians. You can show that k-local Hamiltonians are sparse for a sparsity that's not too high if the locality is not too high. As I said, you can give efficient simulations for them. They maybe don't as naturally describe kind of systems. I mean, it's a much bigger class of Hamiltonians, and so most of them kind of won't necessarily correspond to kind of reasonable models of physics. But it's nevertheless kind of a useful class to have available, especially if you want to be designing quantum algorithms for problems that don't necessarily have something to do with physics. But also there are cases where, for example, in some proposals for simulating quantum chemistry, it really is useful to think about doing simulations of this setting of sparse Hamiltonians. It's also useful for sort of understanding some kind of query lower bounds for Hamiltonian simulation, because in this model we really have, we can imagine we have this black box that tells us where the non-zero entries are in the matrix, and we can think about counting queries to that black box to understand the complexity of Hamiltonian simulation. Okay, great. So the next thing I want to do, now that I've kind of said precisely what the Hamiltonian simulation problem is say a little bit about the, kind of some issues related to computational complexity of Hamiltonian simulation. Okay, so how hard is this problem, simulating the dynamics of some given Hamiltonian? Well, it's a little bit hard to even pose this question, precisely the way that I set it up, because the problem as I described it is inherently quantum mechanical, right? You're given a quantum state as input, and your goal is to output a quantum state at the end of the day. Of course, a classical computer cannot explicitly represent that quantum state efficiently. There are exponentially many amplitudes in it, so that's not something that you could really sort of compare. There's not like a fair comparison to make between what the quantum computer is doing, where it gets to have the quantum state loaded into its memory, and the classical computer can't even do that. But you would sort of expect that this problem should be hard for classical computers because of this fact that it kind of can't even represent the quantum state. So how can we actually make a fair comparison where we can really say that somehow the quantum computer can do something that the classical computer cannot? Well, what we can do is we can rather than just give the input state as a quantum state and have the output be a quantum state, we can provide succinct descriptions of the input and the output that will make sense in the classical context. And of course, if we really want to run some computation, we have to have these things anyway. So imagine that we have some succinct description of the initial state that allows you to prepare it. So for example, it could be some small depth quantum circuit that would prepare that state. That gives you some description of what the initial state is. Maybe we have also some simple final measurement we want to make. Let's say we're just going to measure the qubits at the end of the day in the computational basis. And imagine that the Hamiltonian also is, for example, it's k-local, so it's something that we can explicitly specify. And now all of the sort of aspects of the problem are things that we could in principle present to a classical computer. So in this setting, a quantum computer, of course, can still efficiently sample the output distribution, right? It can prepare the initial state, it can perform a measurement on the final state, and then it can sample from this distribution. And so we can ask, how hard is this for a classical computer? And the answer is, it's hard as long as you believe that there's anything a quantum computer can do that a classical computer cannot. Right? So if there's any problem that has quantum speed up at all, then this problem is a hard problem for a classical computer. Because this quantum simulation problem is what we call BQP hard, it's a problem which is as hard as anything that a quantum computer can do efficiently. And this really follows from actually one of the kind of very earliest results in quantum computing, which was in this paper that Feynman wrote in 1985, which, I mean, actually in this paper, he was thinking about how you would realize reversible classical circuits with a quantum mechanical Hamiltonian. But you can just plug in quantum gates into the construction that he gave and immediately see that you can actually implement general quantum circuits by the dynamics of some Hamiltonian. So the idea as follows. It relates to these things called clock constructions that have actually been super useful in many areas of quantum computing and quantum complexity. What we want to do is we want to take the action of some quantum circuit and we want to encode it into the dynamics of some quantum Hamiltonian. And the way you can do that is to write down a Hamiltonian whose terms correspond to the action of the gates in the circuit together with advancing a clock. So we're going to have a register in our system that records kind of the time at which these gates are applied. And we can have terms in the Hamiltonian where we advance the clock from step j-1 to j, and we apply the jth gate. And of course, the Hamiltonian has to be Hermitian, so there has to also be a term where you go in the other direction, where you go from time j back to time j-1, and then you undo the gate. But you can sum up all these terms, and maybe you want to have different coefficients for the different terms. There's actually kind of a technical reason why maybe you don't want to just add them all up, but you want to choose these coefficients carefully. But anyway, that then defines some quantum mechanical Hamiltonian that where the evolution according to that Hamiltonian will have some correspondence to implementing the quantum circuit. Okay, so if you actually make a careful choice of these alpha j's, and maybe there's not time to go into the details, but it turns out that there's a sort of a careful choice that you can make for which the evolution of this Hamiltonian will actually exactly perform the computation. It will advance the clock from time 0 to, let's say, time k if there are k gates, and it will apply the unitary u that you get by sort of applying all of these gates. Right? So this is, I mean, it's maybe not super surprising. This is just saying that you can realize quantum circuits by some quantum Hamiltonian. I mean, of course, if like the Schrödinger equation is what describes physics, and you believe you can build a quantum computer, then you should be able to do something like this. But this is a nice construction that really does it very explicitly and cleanly. And in fact, if you sort of think about how to implement this clock register in the right way, you can even do this in a way where the Hamiltonian is very local. So if this is a circuit of, let's say, 2-qubit gates, you can do this in a way that this Hamiltonian is just 4 local. So it doesn't need to have really highly non-local interactions. This is not, I'm not claiming that this is geometrically local, but it's local in the sense of the interactions acting on not too many qubits. Okay, so this sort of shows us that any quantum circuit that we could implement, we could also realize by some Hamiltonian dynamics. And so this circuit could be the circuit for running Shor's algorithm, right? It could be a circuit for factoring, which is a problem that we think is hard for classical computers. And so there's some corresponding Hamiltonian that will basically implement what the factoring algorithm does. And if you could simulate those Hamiltonian dynamics with a classical computer, you could factor, right? And so you can plug in, any quantum circuit you like here, get some Hamiltonian. And so this kind of shows us that these Hamiltonian dynamics in general are, as hard as anything a quantum computer could do. Okay, so surely Hamiltonian simulation is hard, right? It really is something we don't expect there to be a classical algorithm for in general. Okay, I want to mention one other sort of complexity kind of result related to Hamiltonian simulation that will motivate some of the algorithmic questions that we think about later on, which has to do with the cost of simulating Hamiltonian dynamics for some given evolution time. So there's this thing called it sometimes goes by the name the no fast forwarding theorem, which says that if you want to simulate the dynamics of some Hamiltonian acting for time t, you need a number of gates that grows at least linearly in t. And I think this is very intuitive. Somehow, you shouldn't be able to kind of fast forward through the dynamics of a general Hamiltonian. One way of seeing that with a sort of like query complexity kind of result comes from a reduction involving the hardness of computing the parity problem. Right? So the parity problem is, this is very simple. You have a bunch of bits, and you want to know, is there an even number of ones or an odd number of ones in this string of bits? Right? So this is a hard problem. Classically, if you want to know the parity of a bunch of bits, you have to know all the bits, right? You can't, the last, if you don't know the last bit, it can change the parity. And so if you don't know all the bits, of course, you don't know what the parity is. In fact, even with a quantum computer, you basically need to query all of the bits. Well, actually only sort of half the bits for a reason that's kind of interesting, but definitely you need a number of queries that's like linear in the number of bits. So you can prove that. If you have sort of black box access to the bits of this string, then computing the parity of all of those bits needs a number of queries that's linear in the number of bits. This has been known for a long time. And so there's a way of sort of describing a Hamiltonian, a sparse Hamiltonian, that encodes the parity such that simulating the dynamics of that Hamiltonian will allow you to compute the parity. And the way that that works is as follows. So we're gonna have a graph that's basically just two kind of disjoint paths of length n. But the way it's going to be designed is as follows. So the edges that go from one pair of vertices to the next pair of vertices here are going to go straight across if the corresponding bit is a 0. But if the corresponding bit is a 1, we're going to put in a cross. Right? So this is a graph that we can define from this bit string. And if we have query access to the bits of this string, then we can understand sort of locally what this graph looks like. Right? And that's enough to run Hamiltonian simulation algorithms, right? If we have that kind of description of the input, we can actually simulate the dynamics of like the adjacency matrix of this graph, or like a weighted adjacency matrix of this graph. Okay. And now you see that there's information about the parity in this graph. Namely, if you look at which vertex over here is connected to this vertex, it's exactly given by the parity, right? In this case, I guess there's an odd number of crossings, and so if you follow this path, you're going to go up here, right? So you're going to be connected from here to here if the parity is odd, and from here to here if the parity is even. And so what that means is if you time evolve the Hamiltonian, let's say, starting at this state, you're going to end up here or here, depending upon whether the parity is even or odd. And actually, if you there's again a thing where we can choose some coefficients kind of carefully and make it that we will, rather than come over here with some amplitude, actually exactly come over to the other end of the path. And you can do that in such a way that if you kind of evolve this Hamiltonian for time, which is linear in the length of this path, you can solve this parity problem, right? And so what this tells us is that any simulation of the Hamiltonian dynamics have to use a number of gates that's at least linear in n, which in this case is t, right? So what this is really telling us is that in general, there can't be a way to fast forward the dynamics, because if for this problem we would be able to fast forward the dynamics, we would be able to compute the parity in an amount of queries that would violate this lower bound. Yeah. Right. Yeah. Yeah. So of course. So yeah. So this statement sort of certainly can't hold for times that are like, um, for completely arbitrary times, right? But in general, we're interested in systems, that have a sort of exponentially high dimension, and this recurrence will be something that's going to be, exponentially high. So yeah. I mean, this is sort of, um, I guess there's some caveats to this statement. This has got to be in some regime where you haven't reached this recurrence time, but the recurrence time is such an astronomically long thing that that's not going to be relevant to applications. But yeah, it's a good point. Oh yeah, that's a good question. There's a paper about this. I forget exactly what the result is. I mean, somehow intuitively you shouldn't be able to really parallelize, because yeah, somehow um, uh, it's a sort of sequential kind of thing. Like you need to have the state after you've evolved for a bit to continue to evolve for the next bit of time. And I think you can prove bounds like this. I don't have like the result at my fingertips, but I think I could find the paper. Yeah, I think there's a result basically saying this. Okay, great. All right, so so that's maybe sort of saying something about what we know about the hardness of Hamiltonian simulation problems, the hardness of simulating quantum dynamics classically, and something about the limitations of even quantum algorithms for simulating Hamiltonian dynamics. So what I want to do now is talk a little bit about some of the methods that are known for simulating Hamiltonian dynamics on quantum computers. So I'm going to start by talking about product formulas, which are a really natural approach to this problem. And it's pretty simple to describe what's going on here, but actually there's some, I want to also talk about some fairly recent developments in sort of understanding the performance of these product formulas that shows that they actually perform quite a bit better than was sort of initially understood. Yeah, after this I'll talk about sort of approaches that go beyond this product formula idea. Okay. All right, so this idea of sort of simulation with product formulas, or it's also sometimes called trauterization, goes back to this paper from the mid-90s by Seth Lloyd, where he gave sort of like an explicit quantum algorithm for simulating Hamiltonian dynamics using this idea. So the idea is as follows. So imagine that we have a decomposition of the Hamiltonian into a sum of terms. We might be given this because maybe the Hamiltonian is k-local and we have a description of what these individual terms are. This kind of idea of breaking the Hamiltonian up into simple pieces, though, is also useful in other contexts. For example, if we have a sparse Hamiltonian, there's also a natural way of decomposing it into terms that are in some sense simple, where the evolution according to the individual terms is easy to implement. But now the goal is just to somehow combine simulations according to the individual terms in order to give a simulation of the overall dynamics. Right, so that's the problem. And there's a kind of really simple thing to do, right? So the issue here is that, of course, if the terms are non-commuting, which they have to be for things to be interesting, you can't just combine evolution according to the separate terms completely independently and have an accurate simulation of the dynamics, right? I mean, if you take e to the a times e to the b, that's not the same thing as e to the a plus b, right? But what you can do is you can slice up the evolution to small segments and alternate between the terms. So in this case where we just have, let's say, h equals a plus b, you can evolve according to a for a little time, let's say t over r, evolve according to b for a little time, t over r, and if you go back and forth a total number of times r, then in the limit that r goes to infinity, you're going to reproduce the dynamics. This is this Lie product formula. And now, of course, in a simulation algorithm, we don't want to take an infinite amount of time. We don't want to use an infinite amount of steps. But we can truncate this to a finite value of r, and we can try to work out how big r has to be in order for this to be an accurate approximation, like to within some epsilon. And so it's pretty straightforward. Basically, you can just kind of Taylor expand. So if we, in this case where we have two terms, if you Taylor expand, the kind of ideal expression, okay, this is the Taylor series expansion. And if you Taylor expand, let's say the left-hand side for like r equals 1, we're going to imagine that t is a small quantity. So we could think about this t being, if you like, this t over r. So let's Taylor expand this expression. Well, then what you find is that the first order terms actually agree, right? The first order terms are the same, and then there's something different in the second order terms because in the real second order term you have a and b occurring in both orders, but of course in this expression you can only have a on the left of b. Right? So you make a mistake at second order, but you have the right thing at first order. And so, what that means is that, these expressions are the same up to terms of order t squared. And so if you kind of plug that into this sort of expression, what you find is that the error in approximating, the right-hand side by the left-hand side is order t squared over r. And then if you want the error to be epsilon, you should take r to go like t squared over epsilon. Okay, so this already kind of gives us an algorithm for simulating the Hamiltonian dynamics, but it's a little bit unsatisfactory because the scaling is like t squared, and also because it's like 1 over epsilon. And we would like to get the best possible scaling with respect to both t and epsilon, right? So this idea of like trying to make the scaling be as good as possible as a function of both t and epsilon has driven a lot of research in algorithms for this Hamiltonian simulation problem. And one very simple way you can make things better with respect to both t and epsilon is to use higher order approximations of this exponential, to use a kind of a more complicated formula here. So this is an idea that has been considered now for a long time in the quantum simulation literature, and which really goes back even earlier to work of Suzuki, who constructed these higher order approximations of matrix exponentials. So for example, there's a second order formula, which is actually really just like a slight tweak of the first order formula, which looks like this. Instead of just evolving according to A and then evolving according to B, we evolve according to A for time t over 2, then B for time t, and then A for time t over 2. And this, it turns out, is going to get us one more order. And Suzuki actually constructed expansions to arbitrarily high order. The construction looks something like this. So you evolve according to, so we're going to start with some base formula, which is going to be this S2. And then the way we're going to construct higher order formulas is it's going to be recursive. And we're going to sort of take this base formula, we're going to evolve it for some time, pk times t, where we're going to choose this pk carefully. And then, we have, and actually we're going to do that twice. And then there's some other parameter qk. I guess the details are not super important, but there's some way of writing out some kind of form of an expression where you can then solve for these coefficients pk and qk such that you actually get an accurate, an even more accurate approximation of the matrix exponential out to order 2k plus 1, right? So yeah, Daniel.
So I mean, this is a heuristic, right? Because A and B are operators.
Mm-hmm.
So in principle, they can be acting on over the space.
Yes.
Error that the error is proportional to higher power of the operator.
So you're concerned about errors in the implementation of the individual terms of, like, let's say, the evolution according to A? Like, what if I make a mistake?
I mean, if you want to balance error carefully, you have to use some operator.
Yes, that is indeed what you can do. Yeah, right. So here when I write plus big O of something, I really mean that somehow, this is shorthand for like the spectral norm of this thing minus this thing is big O of this. And in fact, you can even give explicit constants.
Powers of the dimensionality.
You can give bounds that will have explicit constants and will take into account any sort of dimension-dependent factors.
Yeah, I was just asking, presumably there are some.
Yeah.
Like, for example, I guess you need the Hilbert space is big, the more steps.
So I think if the norms of the terms are big, then you will need to take more steps, but there won't be sort of inherently dimension-dependent factors. I mean, if the norms of the individual terms are growing with the dimension of the system in some family of Hamiltonians, then yes, absolutely. There will be some dependence on norms of the terms. And in fact, what I'm going to sort of explain in a little bit is that actually somehow what matters is not so much just the norms of the individual terms, but actually commutators, and for these higher order formulas, nested commutators of the terms. So the norms of those things will matter. If the norms of those things grow with the dimension, then yes, there'll be some growth with the dimension, but somehow there won't be other dimension-dependent factors in the bounds that are known. Yeah. Does that?
Yeah.
Okay, great. Okay, cool. So so you can find these formulas. The way this particular construction works, you always get formulas of even order. I guess there's no particular reason it has to be that way, but that's how this particular construction works. And this allows you to get more and more accurate simulations. So if you do this, if you use this order 2k approximation, and you have some Hamiltonian that has, let's say, L terms, then you can give a bound that scales like this. And So let's see. I mean, so this is a bound on the number of exponentials. So you can think about this as like a proxy for like the number of gates that it would actually take in some simulation to reproduce the dynamics for time t up to error epsilon. And so what you see is that it, and you can really give a bound like this. I think actually even maybe the bound exactly as it's written, with explicit constants, right? So you see in this bound, following up on Daniel's question, like there's not an explicit sort of dimension dependence in the bound, but there is a dependence on the norms of the terms in the Hamiltonian. So these things, of course, if those are big, that's gonna contribute to the number of gates that you need. And so what you see here, let's look, for example, at the dependence on t, right? So this is a factor that's linear in t, but then you have another term that goes like t to the 1 over 2k. Right? So you can make things closer to linear in t. You can make the cost of the simulation closer to linear in the amount of time that you're evolving for, but at the cost of increasing the order of the formula. And there's this prefactor which grows exponentially with k, right? So you're not going to be able to take a really large k because then you're going to pay this exponentially large factor, right? So for any, if you want to get an algorithm that scales like t to the 1 plus, delta, for a delta as small as you like, you can do that. You can give such an algorithm, but you're going to have to pay this factor, and so you're not going to be able to take delta to 0 very fast. Right? Yes. I think the answer is it depends, right? So I think if you really want to push into the regime of evolving for really long times, then you should take really high orders. Right? So you will always, you can make the evolution time large enough that you will always get a benefit from taking the higher order approximation. In fact, for arbitrarily high order approximations. Yeah, well, that's a problem, right? So what that means is that evolution time is going to have to be really, 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 really big before you're going to want to take a very large k, right? Yeah. Okay, great. Okay, so this was sort of like the state of the art in sort of the analysis of these formulas in sort of like the mid to late 2000s. But sort of more recently, there have been better bounds that have been developed that show that actually this can be quite loose, and this sort of came from sort of numerical experiments, which actually suggested that those lower bounds were that those bounds on the error were were actually pretty loose. They were not close to the actual error that you would see in a product formula approximation of Hamiltonian dynamics. And sort of the kind of technical tool which led to these better bounds is this kind of notion of what's sometimes called local error analysis. Basically, the idea is to give some kind of integral representation of the error. So let me show you like the simplest such expression. This is a way of sort of understanding what's going on when you have two terms in your Hamiltonian and you're looking at the first order approximation, right? So this is the exact evolution, and then this is the kind of like first order approximation for some time t. This will be a good approximation if t is small. And so what you can show is that you can actually exactly represent the error operator, like the difference between the ideal and the approximated evolution, by some kind of integral. And what does this integral look like? Well, it's an integral of the commutator of the terms in the Hamiltonian conjugated by a bunch of stuff, and you're going to integrate over these times. But crucially, these terms that appear to the right and to the left of the commutator are just unitary evolution. Right? So those are things of norm 1. So what this allows you to say is that if you take like the norm of this and you just apply the triangle inequality, well, actually, the norm of this error operator, sort of the error that you make when you try to approximate this by this, is at most, and this is really true with no sort of other constants that depend on anything, t squared times the norm of the commutator between a and b. Okay. So this tells you that sort of you can give a bound that doesn't just depend on the norms of a and b separately, but depends on their commutator. And if their commutator is a lot smaller than like the product of the norms of a and b, this can be a much better bound. So this is nice because it has it gives you this commutator scaling. Also, this is somehow capturing the effect of all the higher order terms. Like they're all in there, right? So there are all these cubic and fourth order, et cetera, contributions that in principle you have to add up. but we don't have to sort of explicitly sum over those. And this can give us kind of much better performance for algorithms for Hamiltonian simulation. And actually, this kind of idea can be generalized to give bounds for kind of arbitrary product formulas that depends on, commutators that, if you consider higher order formulas, you have to nest out to higher levels. So here's something you can prove. So if you consider a pth order approximation of the dynamics, then the error will be like, well, OK, so it'll go like t to the p plus 1 if it's a pth order approximation. But the kind of error will scale like the sum of these sort of nested commutators, where you sort of take all possible ways of taking commutators between all of the terms that appear in the Hamiltonian. And this can give us, a much better approximation of the dynamics. So this is kind of like the bound you would get on the number of gates that it takes to simulate the Hamiltonian for time t. And this really gives us much tighter bounds, which, I'm probably not going to have time to talk about the sort of specific applications of this later on. So let me maybe just mention now that, for example, if you would want to simulate systems that have geometrically local interactions, then this will actually save you like a pretty significant factor, like a factor of the system size, roughly, relative to kind of what you would get without using these bounds. So this hopefully gives us much better bounds that will allow us to, and notice that like we're not changing the algorithm, right? This is not a better algorithm in the sense of like approximating the evolution differently. We're just giving a better analysis of the error in a particular algorithm. So you can sort of just do what you would already maybe have been doing, but this analysis of the error allows you to use bigger time steps basically, and still have a theoretical guarantee that your error is going to be small. Yeah. I think it highly depends on what the Hamiltonian is. Yeah, I don't have a succinct answer to that question. Yeah, right. So another question is, how hard is this to compute? And in general, it could be kind of hard to compute. One question which is maybe interesting, which I thought about a bit, has to do with, like, well, what if you have a translation invariant system, right? Then in principle, somehow everything is specified in a very concise way. Maybe you can compute these bounds. I mean, then you really should be able to do a computation with an amount of work that doesn't grow with the system size at all, that tells you what this bound is. And there are sort of ways of doing that. So you can imagine in some situations being able to use this bound without having to do kind of an exponentially hard computation. But yeah, definitely in general, like that is an issue. Like, how do you actually compute this, exponentially large sum? Yeah. Okay, good. Other questions? All right, great. So next I want to talk a bit about some of these kind of post-Trotter methods. And I know that Ewan, in her talk, introduced some of these ideas related to quantum signal processing. So, but what I would like to do is, at least describe some of the ideas that maybe led up to this concept of quantum signal processing, which I think maybe will provide a bit more context for what some of these methods, where some of these methods came from, and what it is that they achieve, and what are also some of the kind of technical ideas that go into them. Okay. Right. So, we have these algorithms which kind of get, in some sense, kind of close to simulating dynamics for time t with a number of gates that's linear in t, but not quite, right? It's like, there's t to the 1 plus delta, and as we saw, you can't take delta to 0 very fast because of this exponentially growing prefactor in the cost of sort of implementing these higher order approximations. And so, a natural question is, can we give an algorithm that just has complexity linear in t, just linear in the evolution time? Somehow, it would be very nice to be able to do that. Somehow, it feels like it, ought to be possible. And something sort of in favor of thinking you ought to be able to do that is that, the system is simulating itself in, time t, right? I mean, if it's evolving for time t, it takes time t to do that, right? And, so that seems like somehow it ought to be possible. On the other hand, maybe somehow this is just inherent. Like, maybe it's not possible to, in the setting that we're considering things, really give a simulation with a number of gates that's linear in t, because there's this like mismatch between the models, right? The Hamiltonian simulation is happening in continuous time, but we're trying to simulate in this discrete time circuit model, and we have to somehow, write down some sequence of gates that implements the evolution. And maybe this mismatch, leads to some slight overhead, and somehow we just have to live with it. So it turns out we don't have to live with it. We can actually give a simulation that's really linear in t. And the way that it was first shown that you could do that is as follows. So you can actually define a sort of like a thing called a discrete time quantum walk, but that corresponds to some given Hamiltonian that you want to simulate. So the way that this so this quantum walk is going to be basically like a unitary operator that's going to be easy to implement and that's going to encode some information about the Hamiltonian. So what we're going to do if we've got some Hamiltonian, let's say it's a sparse Hamiltonian, H, we're going to define a unitary operator acting on a larger system. So now we're going to have two registers of dimension, basically the dimension of the system that we're trying to simulate. And one operation we're going to do is we're going to reflect about the span of this set of states. So these are states where there's a state basically like for every row of the Hamiltonian. The first register has this kind of ket j that sort of labels the row that we're talking about. And the second register is this particular superposition of the elements living in the jth row of the Hamiltonian. It involves these like complex conjugates of the square roots of the entries of the Hamiltonian, but it doesn't matter so much. It's just some particular quantum state that you can efficiently reflect about if you have a description of this H as a sparse Hamiltonian. So this is a reflection. You can reflect about the span of all these states efficiently if you've got a sparse Hamiltonian. And the other reflection we're going to do is we're going to swap the two registers. Okay, so we're going to have an operation that consists of first reflecting about the span of all of these states and then swapping the two registers. And that's going to be like a step of our walk. It's an easy thing to implement if H is a sparse Hamiltonian. And the thing that's nice about it, aside from the fact that you can implement it efficiently, is that it has information in it about the spectrum of the Hamiltonian. So specifically, you can show that if you've got an eigenvalue lambda of the Hamiltonian, then there are going to be two corresponding eigenvalues of this larger thing. And then there's also going to be there's like some other part of the space that we're not going to care about. But in particular, there are going to be, for every eigenvalue lambda of H, there's going to be two corresponding eigenvalues of this operator that's defined here that are like e to the I times the arc sign of lambda, and then two different ones with different plus and minus signs. And the eigenvectors also are somehow closely related to those of the Hamiltonian. And so what you can do basically is if you've got some evolution that you want to implement, so you would like to implement the operator e to the minus I ht, well, what you can do is, let's say for the part of the space where you have the eigenvector with eigenvalue lambda, I've denoted that like this here, you can use this procedure called quantum phase estimation, which uses this operator that you would like to estimate, and is then going to produce in this register an estimate of what the eigenvalue is. And the eigenvalue or the eigenphase of this operator is this like arcsine lambda. So basically, you can come up with some kind of estimate of arcsine lambda. This is like a number that you're encoding in your quantum computer. You're writing down an estimate of arcsine lambda here in this register. Okay, but that gives you some specification of what lambda is. And so what you can do is you can perform also a unitary operation that applies the phase e to the minus I lambda t, which is exactly the phase that should be applied in the part of the space where you've got the eigenvector with eigenvalue lambda. And then you can uncompute the estimate. You basically do inverse phase estimation to uncompute this estimate. Okay? And if you work out what is the cost of doing all of this, you can show that actually you only need a linear number of steps of the walk to simulate the Hamiltonian evolution for time t. Right? You basically, the sort of precision with which you need to estimate these phases in order to get the evolution accurate to time t is such that you can do this with a number of steps that's really exactly linear in t, and we can really meet this lower bound of this no fast forwarding theorem. Now the scaling with epsilon is as is written here, it's like 1/squared of epsilon. That's not, it turns out that that's not the best that you can achieve, but this is an algorithm that gives this kind of like best possible scaling with the evolution time. Okay. Yeah, it has to be sparse, but if it's local, then it's sparse. So you can do this in particular for local Hamiltonians. So it's actually pretty general. Yeah, you can worry about the overheads with the locality and that those things are not captured here. I definitely don't claim that this is a particularly like useful algorithm in practice. That actually these things like this idea of quantum signal processing are like definitely better algorithms to use in practice. But this is like how it was first shown that you could actually give evolution with time strictly linear at t. And this idea kind of relates to what goes on in quantum signal processing. Okay, so another question that you can ask, which I think has also driven a lot of kind of research on Hamiltonian simulation algorithms, is what is the best you can do as a function of epsilon, right? So we had this no fast forwarding theorem that said the best you can do as a function of t is linear in t, and we have now achieved that, right? But what about epsilon, right? So we have lots of things that can be done, lots of sort of approximate computations that can be done to kind of within epsilon with poly log 1 over epsilon overhead. And so that would be a nice kind of thing to be able to achieve. But that's very far from what we have so far. On the other hand, what can you say about the sort of limits on what you can do? So it turns out you can show, again using a sort of a lower bound, a query lower bound related to this parity computation problem, that if you want to simulate the Hamiltonian dynamics within error epsilon, you need at least this many steps. You need a number of steps that grows at least like log 1 over epsilon, actually over log 1 over epsilon. And the way that this works, I mean, actually, again, relates to the things that are known about the complexity of computing parity, but now for like the unbounded error query complexity of parity. So if you want to compute the parity of a bit string, even if you want to be able to get a very slight advantage over random guessing, even that is very hard, right? So there are bounds that sort of say that even that is very difficult. And so you could give sort of like a kind of inaccurate simulation of the dynamics and still be able to get maybe some advantage against random guessing for computing parity. Even that is something that shouldn't be possible, and that allows you to establish limitations on the number of steps that you need to compute to simulate the Hamiltonian dynamics, and the bound that you get is exactly this. Okay, on the other hand, what we can actually achieve is quite far from this lower bound, right? So there's this quantum walk simulation that I mentioned that scales like 1 over root epsilon. If you take product formulas and you use higher order product formulas, you do better. You can get sort of an arbitrarily high power of 1 over epsilon. So you can get the scaling to be better and better with epsilon as you take higher and higher order formulas. But this is still sort of not achieving this log 1 over epsilon. I mean, in practice, you really should sort of imagine the best you can hope for because of this exponential factor is something like this for some large but constant value of k, and that's scaling like something that's polynomial in 1 over epsilon. Whereas the question is, can you get close to this lower bound where the scaling is like log 1 over epsilon? No, I think it makes it better. Because, yeah, so this is the complexity. So 1 over epsilon is some, oh, sorry, sorry, this is minus 1 over 2k. Yeah, maybe right, sorry, I think there's a typo. Sorry, sorry about that. Yeah, I understand your confusion now. Okay, sorry about that. Yes, right, it does get better as k gets bigger. But it's not going to give us, this log scaling. Yeah, it should be 1 over 2k here. Okay, right. So this is the question: can we do better? Can we sort of get closer to achieving this? It turns out we can actually achieve this. We can actually give a Hamiltonian simulation method, not using these product formulas, but using some other ideas, which really get us all the way down to this log 1 over epsilon. Even with the denominator, the log 1 over epsilon denominator. Okay, so the way that this was first shown is as follows. The idea is something that's actually, I mean, it's kind of like a straightforward thing to kind of think about trying to do, although it's not clear how to actually achieve it. It's also maybe not so clear why it would be necessarily a good thing to do. But the idea is really just to directly implement the Taylor series of the time evolution operator, truncated to some finite number of terms in the series. So what we're going to do is we're going to take the time evolution operator, we're going to truncate it to, let's say, capital K terms. And now what we're going to do is we're going to decompose the Hamiltonian into a sum of terms. And for technical reasons, we're going to do this in a way where the individual terms happen to be unitary operators. You can do that. So for example, if you have a local Hamiltonian and you decompose into a sum of Pauli operators, then you kind of naturally get operators that happen to be unitary. Yeah, there's other ways of doing this. So let's imagine that we can do that. Well, then what we can do is we can plug this expression back into this truncated Taylor series, and we get something that looks like this, an expression like this for the evolution operator, which is a linear combination of unitary operations with some coefficients, these alphas and also some phases. Okay, so it turns out that you can, and there's actually sort of like a general thing you can do on a quantum computer. If you have an expression for a unitary, or approximately, in this case, approximately unitary operator as a linear combination of unitary operations, you can implement that with some cost. And the cost is exactly like the one norm of the vector of coefficients of the terms, right? So here, these vj's are unitary. The u is and they're unitaries that are easy to do. The u is this unitary operation you would like to apply, and then there are all these coefficients. And it turns out that you can implement this u with a cost which scales like the one norm of this vector of coefficients. And you can really do this in a nearly deterministic way as long as this u is close to unitary, which it is in this case because we're truncating this Taylor series of a unitary operator. OK, so the main ideas that go into this involve sort of first implementing u with some amplitude, so in the sense that's written here. So we're going to perform some operation that, we're going to have kind of this control register which starts out in the state 0, and then there's going to be an amplitude here, it's written as sine theta, with which that register remains 0, and we apply u to the other register. But then we're going to have some other part of the superposition where we do something else. There's some orthogonal part of the state which occurs with some other amplitude cosine theta. So this is like, in some sense, like partially implementing u. But what we would like is to pick out just this part of the superposition. We would like to amplify this term. And it turns out that there's a way of doing that by some kind of process which is kind of related to amplitude amplification, which is some kind of abstraction of what goes on in Grover's quantum search algorithm, but in a way that works in this context where somehow you're not able to do the thing you would have to do in ordinary amplitude amplification, namely to reflect about the initial state. Right? So one of the operations you have to do in the amplitude amplification algorithm is a reflection about the initial state. In this case, we want to start from this state where psi is an unknown quantum state. We want to do quantum simulation on psi, and we don't know what psi is. So in particular, we don't know how to reflect about it efficiently. But nevertheless, there's a procedure which is somehow oblivious to what psi actually is, which is able to just boost this part of the state. Okay, so let me maybe very briefly kind of describe what kind of goes into these two ideas of sort of implementing u with some amplitude and then boosting the amplitude for success. Oh, and yeah, I should say, so the query complexity when you do this is going to scale like this. So in particular, for fixed t, it's going to give us exactly this log 1 over epsilon over log 1 over epsilon. This expression basically comes from understanding kind of like how big does k have to be before this is a good approximation of the exact evolution operator. And it turns out that it has this good scaling with epsilon that goes, exactly meets the lower bound that I mentioned before. The scaling with t is actually also not too bad. So it's not linear in t. It's like t log t over log t, but it's only a little bit superlinear. It's better than anything you can achieve with product formulas, and it's not so far away from exactly linear.
Query complexity, that different complexity is actually doing the simulation.
Yeah, so good. So you can achieve this query complexity, let's say for sparse Hamiltonians, but you can also get the sort of gate complexity to be this within sort of logarithmic factors, like factors that are like logarithmic in the system size. So you can also get close to this for the gate complexity for either for the sparse case or if it's really an explicit local Hamiltonian. Yeah, you can really get basically this. Yeah, it's not just a query complexity result. You could imagine actually using this in practice, although in practice, if you want to do something like this, you should really do this quantum signal processing stuff. Like it will be more efficient. Yeah. OK, so yeah, let me very briefly mention how this these two ideas work. So how do we perform this partial implementation? So we have some decomposition of u as a sum of unitaries, so what we're going to do is we're going to sort of consider a quantum state that encodes the amplitudes, encodes the coefficients in this linear combination in the amplitudes of the quantum state. So specifically, it's going to encode the square roots of these betas, and then for this to be a normalized state, the factor that we need to normalize by is exactly the one norm of the vector of coefficients. That's where this arises as kind of the complexity of this procedure. And then we're going to consider this operation that sort of prepares this quantum state out of the 0 state. So that's what this B does. And then it's going to perform this select V operation, which conditioned on the first register storing J is going to apply the operator Vj. And then we're going to kind of unprepare this state. We're going to map this state back to 0. So this B is like a unitary operation that maps 0 to this thing. OK, so then what we can do is we can think about doing this. So we're going to start with this ancilla register being in 0. We have our state that we want to simulate, psi as input. We're going to apply this step W, and then we're going to look at the piece that we get if we project back on the 0 state for the first register. We're not going to do anything to the second register. This is just the identity operation. And then, so you can do a little calculation, and maybe in the interest of time, we don't have to step through it sort of slowly. But what you can find is that if you do this, what you get is exactly 1 over s times the unitary applied to psi. And what that means is that, well, what is this W doing? Well, it's implementing U in the sense where, there's this register flagged by 0 where we apply U to psi, but only with an amplitude like 1 over s. That's this normalization factor. And then there's going to be some other kind of orthogonal term in the superposition, right? And so this operation, this is something that's kind of like easy to do. If we have the ability to apply these V's, we can use that to implement this select operator. And then this B is just some explicit thing, which is, not depending on the V's. It just depends on these coefficients. And so if you know what these coefficients are, then, this B is an operation that you can find a way to implement. Okay, so this is a way of, in some sense, implementing this U that we would like to do. But of course, in general, with, it's going to be scaled down in some way by this parameter s. If s is very large, then we're going to have only a very small piece of the state in which we actually did the thing that we want. So then what we have to do after this is to boost, to try to get the, this piece of the state to actually be the whole state. Okay, and that's this oblivious amplitude amplification. And this is really a lot like amplitude amplification, kind of ordinary amplitude amplification, if you're familiar with that in quantum computing. But the issue is that we have this unknown input state, which we don't know how to reflect about. And so we can't just do the thing we would do in ordinary amplitude amplification. So what we're going to do instead is, something analogous that's going to turn out to work. So the way this is going to work is basically we're just going to replace the reflection about the initial state in ordinary amplitude amplification with this reflection, where we reflect just about the 0 state of the first register. And then what we're going to do is the following. So we're going to think about sort of applying this operation W that implements U with this amplitude 1 over s. But then we're going to do the reflection. We're going to undo W. We're going to do another reflection. And we're going to do another W. And OK, there's a calculation you can do, which again, in the interest of time, maybe I won't kind of go through carefully. But what you can show is that in this case where U is approximately unitary, then what happens, when you do this procedure is basically you implement U sort of in this piece of the space where the state starts out as 0 and then comes back to 0 at the end. You're going to implement U with another coefficient that now is no longer 1 over s, but is this expression. It's 3 over s minus 4 over s cubed. So you're implementing this U with a different coefficient. And in particular, if we can sort of tune things so that s equals 2, which in the Hamiltonian simulation problem you can do because you can adjust what this s is going to be by taking shorter and shorter evolution times. So we can get into a sort of a regime where, by tuning things, we can make this s to actually be, let's say 2. And if s is 2, then what we do is we boost the amplitude from, it was initially 1/2 of s equals 2, and we can boost it all the way to 1. And this is just, if you're familiar with like how the Grover algorithm works or how amplitude amplification works, this is exactly like the case where kind of one step of amplitude amplification will take you from a success probability of 1/4 or an amplitude of 1/2 to perfect success, right? So we can sort of like amplify things all the way up to definitely succeeding. Okay, so this is a procedure that we can use now to sort of take this like imperfect implementation, make it perfect, and and then sort of implement the simulation. Yeah. So okay, so I think that there's a way of getting this complexity, which if I go back, right? So our goal was to kind of get. Sorry, where is it? Oh, there it is. OK. Yeah, our goal was kind of to get this complexity for Hamiltonian simulation. And I think what you can do is you can, specifically to get this, I think you can actually do it where you only ever have to do one step, in the individual segments. You only have to do one step of this oblivious amplitude amplification. Because what you can do is you can slice up the evolution into really short time segments. And by making the evolution time really small, you can make it that you kind of, you're already pretty accurate, right? And somehow, of course, you're going to pay something in terms of the fact that there's error in the individual segments, and you need the accumulated error over many, many steps, which if you're taking the steps to be very small, will indeed be, very many. You need the accumulated error to not be too big. But the way the sort of, dependence on the error here is only logarithmic. So somehow you can suppress that in a really efficient way. Yeah. So yeah, I mean, there are different ways you could imagine applying this, but the sort of like simplest way to get this in complexity doesn't just do one step that goes all the way to the end of the evolution. It divides the evolution up into segments, does each of those very, very accurately, and then just strings them together. Yeah. And that's actually maybe some of the origin of the inefficiency of this algorithm, or somehow its failure to achieve like the best possible complexity. Right. So right. So now we have this algorithm that sort of achieves this best possible dependence as a function of epsilon, but it doesn't at the same time achieve the best possible dependence on t. It gives sort of like this complexity. And so now another question we can ask to try to maybe drive sort of like more advances in kind of quantum algorithms for Hamiltonian simulation is what can we do in terms of the trade-off between t and epsilon, right? So we have different algorithms that are separately optimal as a function of t or optimal as a function of epsilon. We have this trade-off between t and epsilon, which is not too bad. But if you sort of put together the information we know about lower bounds, kind of the lower bound that you get is like the larger of t and log 1 over epsilon over log 1 over epsilon, which asymptotically scales like this, like the sum of t and this expression. Right? So this is like a lower bound that we know, and the complexity of giving a simulation for time t with error epsilon. And this is like an upper bound that we have. And we would like to close this gap, right? I mean, what is really like the best we can do as a function of t and epsilon together? And so it turns out that actually you can basically achieve this lower bound. So there's another Hamiltonian simulation method, which combines ideas from some of the methods that I've mentioned already, that really gives complexity that's basically like this, kind of all the way down to like t plus log 1 over epsilon over log 1 over epsilon. And this method is what goes by the name of quantum signal processing. It really achieves this kind of like optimal trade-off. The main idea of this approach is somehow actually not to do this thing of like dividing up the evolution into a bunch of small segments, but really to try to go all the way to the end in one step. And the way that it's going to do that is it's going to somehow encode the eigenvalues of the Hamiltonian into some two-dimensional subspace. So we're going to work kind of separately on each of the eigenspaces of the Hamiltonian. And then within that two-dimensional subspace corresponding to each of the eigenvalues of the Hamiltonian, we're going to have some process that's going to allow us to manipulate the eigenvalue. We're going to do some signal processing on the eigenvalue within that subspace that allows us to turn sort of the eigenvalue lambda that we have a handle on into e to the minus I lambda t, right? The thing that we would get if we would perform the Hamiltonian evolution according to h. So there's some kind of carefully chosen sequence of single qubit rotations that you can do within that subspace that allows you to do this signal processing on the eigenvalue to implement it, to manipulate it into the thing that you would like. And it turns out that there's a way of doing this that's works very efficiently and that allows us to achieve this complexity. So maybe in light of the time and also the fact that I think Ewan talked about some of the ideas related to this kind of quantum signal processing approach, maybe I won't talk about the sort of like all of the details of this quantum signal processing method. I mean, they relate to this idea of sort of like block encoding, right? So I think Ewan introduced this. There's this notion of kind of implementing some operator A as kind of the upper left block of some unitary transformation that you know how to apply. We've actually seen an example of a block encoding already, I guess, in this LCU approach, where this kind of 1 over S implementation of U through this operator W, it was basically a block encoding of U divided by S. And then oblivious amplitude amplification is some way of basically boosting that block to be everything, right? So that's a tool that's also going to be useful in building up these quantum signal processing algorithms. Yeah, you can take these block encodings and somehow, you can find a block encoding of the Hamiltonian that you would like to implement,
Very happy
and then you can
today.
basically manipulate that block into e to the minus IHT to implement the Hamiltonian simulation. I think,
You should have the same unless people just
yeah,
decide
maybe I
to
think in light of the time,
leave
yeah,
it and
maybe I
try
will
it.
just
No, they didn't let me know.
not discuss this. But if there, this would be a great thing to talk about, I guess, in the discussions later, if there's interest in, thinking about sort of how this relates to the algorithms that I mentioned before. Okay, so maybe what I will do now is move on to talk about these kind of special topics, and actually maybe I will just talk about one or two of them. Sorry. Yeah, let me just mention one kind of recent sort of result related to these product formula simulations that I think maybe would be of interest. So let's go back and talk a little bit about this idea of simulating Hamiltonian dynamics using product formulas. And I want to talk about sort of what happens if you sort of change the measure of success, change the sort of like notion of error that you're using. Specifically, if you think about what happens on average if you choose the state at random, and then I'll talk about then something you can do for actually particular input states that kind of achieve something similar. Okay, so yeah, we're going to sort of change gears now and talk a little bit about simulation on average, where we're going to choose the state from some distribution. Right, so we had a worst case guarantee, and under this worst case guarantee, using this kind of theory of Trotter error, this way of analyzing the error using local error analysis in order to get a bound on the error that depends on commutators of terms of the Hamiltonian, we had a bound that looked like this, right? So it said if we want to evolve for time t, we could give a simulation that had an error that scaled like t to the p plus 1 if we're using a pth order product formula approximation. And the coefficient of the error is this thing alpha that depends on these nested commutators of terms of the Hamiltonian. But now, what if we sort of think about a different setting where we actually choose the state at random from some distribution over states? And in particular, kind of a natural thing to do is to choose the state according to a one design, right? So I think maybe there was some discussion about T designs earlier in the meeting. So a one design would basically be sort of a distribution over which if you're just given a single copy of the state, you're not able to tell the difference between it and kind of a uniformly random state, right? A Haar uniform state. So this could be there are many kind of simple distributions that have this one design property. Like for example, the state could be a uniformly random basis state, let's say in the computational basis. So it's like much weaker than sort of demanding that the state is actually Haar random. It's it's a weaker thing. There's lots of sort of simpler distributions that would have this one design property. So if we choose the initial state from a one design, then you can show that actually the error in this pth order product formula approximation will scale like a very similar quantity, where again you have this alpha, but it's what I'm calling alpha f. F, I guess, is for Frobenius, because this coefficient that describes the error is going to be exactly the same thing, but where instead of taking the spectral norms of these operators, you take the Frobenius norm, and now you get to divide by 1 over the square root of the dimension of the system. So this is like a thing that's like exponentially big, but it's not really for free, because the Frobenius norm can actually be bigger as well. This is an expression. This alpha f is never any bigger than alpha. So this is actually a bound that's always going to be no worse than this bound, but it can sometimes be better. It can sometimes give a much better bound. And again, like when we sort of came up with this bound in the first place, what we're talking about here is not changing the algorithm, right? When we did like this quantum walk thing or linear combinations of unitaries or quantum signal processing, we were doing a very different algorithm, right? But what we're doing here is we're just using product formulas kind of as we ordinarily would, but we're giving a better bound on the error that they incur, and therefore a better bound on the number of steps we would need of the algorithm in order to give a simulation within some allowed error. Well, we don't have to, but you can show that somehow, in this setting where you imagine that the state is, you have this promise that the state is chosen at random from this distribution, the error can be bounded by this quantity. I mean, yeah, you don't have to. I guess nobody's going to make you, but you can get this better bound, right? I mean, this is still going to be a bound on the amount of error because this is a bound for the worst case. But what you can show is that somehow this Frobenius norm is going to capture like what happens on average, and it could be a much better bound. Yeah, and so for example, like if you have like a nearest neighbor interacting Hamiltonian with n qubits, this will save you a factor of like the square root of n in the error. So it's going to give you a tighter bound in some cases. So if this is what you care about, that the state is chosen at random from this distribution. Yeah, but now something you might worry about is like, well, is there a setting where we're actually going to care about the state being chosen at random, right? I mean, probably if we're doing simulations of physics or something, we're simulating some material, like we're maybe not interested in what happens if we take a random initial state. We have some, natural initial state that we want to consider, and we would actually like the cost of the simulation to be low for that particular initial state. But it turns out that somehow there's a kind of another perspective on this, which allows you to get similar sorts of bounds, but not under, without this assumption that the state is drawn at random from some distribution, but actually just for any kind of typical state. And you might kind of expect this. I mean, intuitively, like if if on average things are behaving in this better way, you ought to have better bounds typically. But we can really make this a little bit more precise. Namely, as long as the kind of marginals of the state on a few qubit subsystems, specifically on the subsystems corresponding to the leading order error terms of the product formula approximation, as long as these marginals are close to maximally mixed, then the scaling will be close to what it would be in the average case. This kind of behavior that these marginals are close to maximally mixed is actually, a pretty generic thing. Like certainly if you would choose the state at random, it would hold with high probability. And it's going to hold as long as the state is highly entangled, right? If we've got a sort of, many body, like reasonably entangled state, it's going to have these marginals being close to maximally mixed. And then you're going to have this better scaling of the error than you would have in the worst case. And in fact, if the state were not highly entangled, it would be easy to simulate on a classical computer, right? We can simulate weakly entangled systems well on classical computers. So like exactly in the case where we want to be using the quantum computer anyway, we should have the kind of states for which we actually get these better error bounds. And so this is nice. It allows you to, again, sort of like for free, without changing the quantum algorithm, get kind of better performance for your Hamiltonian simulation. And here, these plots show kind of, here this is showing empirically what the error actually is in some simple, this is some simple model. It's, it's a reasonably small system, so you can actually just simulate it on a laptop. But you can see that somehow the worst case scaling of the error is, definitely worse than what happens. So one of these curves is what happens when you do things with the state chosen, at random. You are actually looking at the average case performance. And the other curve, which you can hardly tell the difference from it, is where you take some particular input state. I think it's just the all zero state, which is a state that rapidly becomes entangled because this is a system that, is going to, for which most initial states are going to rapidly turn into very entangled states as the system evolves. And you see that you actually have this much better performance of the number of steps that you need in order to get a simulation within some small error epsilon. So this is actually kind of, you actually see this in practice in simulations, and the bounds that we've been able to prove about this, really can sort of like capture this scaling. So that's like what's shown here. Yeah. I think the intuition is that somehow, in the case where the state is chosen at random, it has this one design property. There's this Frobenius norm, which is kind of governing the sort of like behavior of the error. And when but sort of like the only thing that matters really when you do this computation are these leading order error terms, right? And so like as long as the state on the reduced state, as long as the marginals of the state for like the things that are relevant to these leading error terms looks like it would in the case where the state was chosen at random from some distribution, you're going to get the same scaling of the error. Does this kind of, yeah.
There a sense in which the error is
Concentrated in what sense?
Like, could you look at like what the variance of the error is?
Oh, yeah, yeah. You can also give bounds on this variance. And in fact, I think to get, yeah, you can get some good bounds, I guess, under the assumption that the input ensemble actually is a 2 design. So if you have like a little bit better design, then you can give pretty good bounds on the variance as well. Yeah. But sort of these statements about sort of like sort of relating this to the sort of mixedness of the marginals, or sort of the amount of entanglement, sort of many body entanglement in the state. This is really something that holds kind of, without any requirement that the state be drawn from some distribution. So this, yeah, this is, I think, makes things a little bit more practical. Okay, great. So maybe this would be a good point to sort of wrap up, because I think we're kind of just about out of time. Let me kind of finish with a little bit of sort of outlook about kind of where things are headed in Hamiltonian simulation. So I think there are a lot of really interesting questions. So on the one hand, there's a lot of algorithmic ideas that have been developed and introduced to solve various kinds of problems. Many things are like really well understood. Sometimes it feels like kind of all the interesting questions about sort of like, all the interesting sort of algorithmic questions about Hamiltonian simulation maybe have been answered, but I really think that that's not true. Actually, somehow we keep managing to find new sort of perspectives on the problem and new things to do, and I think there's a lot still to be understood, sort of like nice theoretical questions, and also questions that will really maybe be relevant as we actually try to implement these simulations eventually, hopefully one day, on real quantum computers. So for example, just to pick one question from this list, like one thing that is actually not well understood is what's the best possible dependence between t and epsilon if the Hamiltonian depends on time, right? So we have this algorithm that achieves the optimal trade-off for time-independent Hamiltonians, but it does this spectral thing that really kind of relies on the Hamiltonian being a fixed object that doesn't depend on time. And it really doesn't work if the Hamiltonian is time dependent. I mean, then we really have worse bounds on this trade-off between t and epsilon. So that's something that still is not well understood. And I think, also there's a lot of interesting stuff to be done about this idea of using quantum simulation to develop other quantum algorithms and sort of understanding what can be done there. I mean, it's thinking about Hamiltonian dynamics. It's a very different way of thinking about developing quantum algorithms than coming up with circuits. And I think this can be, I mean, it has been, and I think maybe it can continue to be a really useful perspective on how to come up with quantum algorithms. And I think it would be great to think more about ways to actually use some of these ideas from Hamiltonian simulation in order to sort of reason about physics, right? So I mentioned this instance where we were able to prove better Lieb-Robinson bounds by thinking about the structure of some quantum simulation algorithm. And I think there may be sort of other areas in physics where you could imagine that somehow thinking about the kind of decomposition of the evolution operator that you get from these Hamiltonian simulation algorithms, potentially could be useful. I think that would be a really interesting thing to explore. I think another area that I really haven't sort of focused on so much here, but I think is also super important, is to think about how we can actually apply Hamiltonian simulation in, to actually learn about physics by running simulations on quantum computers. There are lots of different kinds of situations in various areas of physics or chemistry or material science where you could imagine applying a Hamiltonian simulation, and there are a lot of details to work out about how exactly to best use Hamiltonian simulation. Lots of different combinations of what algorithm do you use, how do you encode your fermions into qubits, how do you prepare initial states, what do you measure? Lots of questions to explore to understand what are the best ways of learning things about physics by running quantum simulations. And this is something that really, I think, needs, has been worked on a lot, but definitely needs a lot more work to understand better. And I think it'll be really exciting to really, start to see these things put into practice as we actually build devices. So I think, really understanding the best way to apply these simulation algorithms, concretely to answer kind of end-to-end questions about physics is a really exciting frontier. Great. So on the last slide, I just have some kind of pointers to some other places to read about some of the things that I talked about, and also some, lectures about various aspects of quantum simulation that might be interesting if you want to explore any of these things further. maybe I'll stop there.
Any final questions? So what's now in a time-dependent Hamiltonian case?
Right. So I mentioned like these algorithms based on linear combination of unitaries that get like, this like t, log t over epsilon over log t over epsilon. So that totally works in the time dependent case. You can sort of like do this thing where you basically like divide the evolution up into short times. You can use, basically you can use that method and it still gives basically the same complexity in the time independent case. That's, I think, the best that's known.
So in classical algorithms like for simulation, like chemistry or mathematical, is super important is that the method is extensive. That means that actually if you double the system size, but they are not very entangled, that you don't jeopardize somehow what you did there, because you are doubling the thing. And it seems that the only method that you describe that is extensive is the Trotter method, not the quantum singularity decomposition. So can you comment on that, or is that?
I'm not sure that I understand exactly what is the property that you want to hold. So
If you would, for example, simulate two completely independent systems,
yes,
then by making the system bigger, it should not be harder to do it. because they're not entangled at all, the two systems. So it is basically two independent simulations. And the only method that has this is you need to have some exponential. Okay, the exponential of a plus b is exponential of a times the exponential of b if a and b commute. And that seems to be a crucial kind of ingredient for all classical simulation methods. And it seems that all these methods, that the second one you're talking about, quantum singularity decomposition, they don't take advantage of that.
yeah. So yeah, I'm not sure if this is related, but sort of like one question is like sort of what should be the cost of simulating? Let's say if you have a system with local interactions, a system with let's say n spins. What is going to be the cost to do the simulation, let's say for constant time? Or let's say what's going to be the circuit depth for the simulation, let's say for constant time. And I guess it really should be constant, right? This is maybe what you would sort of call extensive, right? Somehow you shouldn't have to do an amount of work that's going to scale longer to simulate the system for constant time just because there's some system way over here. Yeah. So I mean, this I think kind of relates to something that I didn't have time to talk about, but it's this this kind of work, kind of from the Microsoft group. I don't know if you know this paper by Hastings, Kothari, and Lowe, but they sort of looked at exactly this question. So actually, even with the kind of like old analysis of product formulas, before this theory of Trotter error, actually the complexity was not extensive in this sense. Like somehow the depth to simulate an n qubit system for constant time would actually grow with n, according to kind of the old error analysis. So this was actually a problem for all of these methods, for basically like before this paper. And so what they showed in this paper is that actually you can give a simulation which is extensive, I think, in the sense that you're describing, that somehow if you want to simulate this n spin system, you can do it in sort of basically like constant depth using this method that they developed. And the method that they developed is actually it used as a subroutine this kind of quantum signal processing, but it involved sort of stitching together simulations on different pieces of the system in kind of a careful way. So I think actually if you just use quantum signal processing kind of out of the box for the whole system, it also has this problem that it doesn't achieve this constant depth. But so this paper shows how to get around that. And actually, if you use this like theory of Trotter error stuff in the case where you have, in the case where you have local interactions, then you actually get very close to this, like up to log factors, or maybe not log factors, maybe it's like sublinear factors, but like sort of very small factors. You can get kind of quite close to this depth. I think actually also with product formulas using this, but you have to use this like stronger error analysis. Yeah.
Any other question?
Is it not the case that thing? Do it again?